It's good to see so many of you today, not at our usual starting time of 6 p.m., but for a special midday presentation by a very special visitor to our School of Architecture, Professor Nordenson from my hometown, New York City. Professor Nordenson is one of the now structural engineers in professional practice today. He's also a professor of architecture and structural engineering at Princeton. He studied at MIT, UC Berkeley, and was a Gold Fellow at Harvard. He apprenticed with the famed Buckminster Fuller before eventually establishing the U.S. office of Holy Arabian Partners in New York, which he directed for several years until his own practice, Nordenson Associates, established since 1987. In his career, he has collaborated with many of the leading architects of our generation, such as Mervyn Gilhouse and Bill May, Richard Meyer, Yusuf Piano, Stephen Hall, Sejima and Nishizawa Kusana, Yoshi Noguchi, and others. Professor Nordenson is active in teaching and research, as well as professional and public service. For example, he is commissioner of the New York City Public Design Commission. He has authored books on site structural engineers, the Felix Nobel Lectures in 2008, as well as patterns and structures. You see the title of his research. He was the first structural engineer to be awarded the Institute Honors for Collaborative Achievement of the AIA, American Institute of Architects, and he is a fellow of the American Academy of Arts and Sciences. We consider ourselves very fortunate to have this opportunity to listen to and learn from our distinguished guest today. Please extend a warm welcome to Professor
Thank you, and thank you for coming out today. I have a lecture that will move through quickly, since I know you all have studios starting at 1:30. Try not to go over, but people over 5 or so minutes. The subject of the talk is this idea of reading structure. I come from a background in literature. I'm a graduate at MIT, where I studied literature as well as engineering. I have a great interest in practice and also in my teaching and thinking about how one goes about reading structure and reading the way in which it participates in the architecture. So I'm going to start off with a couple of examples and then to a brief review of projects that I've worked on, and then end with a few recent projects. This is also the title and the structure of the book that I've been putting together that hopefully will be published next year. So it's a kind of survey as well of our work. There's a quote that I'm fond of, which Wittgenstein, whose house is in the background, was also very fond of, which is, in the elder days of art, builders wrought with greatest care each minute and unseen part, but God see everywhere. Wittgenstein was really interested in the fact that there are so many aspects to architecture that are unseen that, in many cases, reveal some of the inner meaning. Somebody told me this story, I'm not sure if it's true or not, that in the 50s and 60s in China, when everyone was wearing, men were in particular wearing pretty much the same thing, the practice was to sew on the inside of the collar of the Mao suit, Mao jacket, that you would wear lace, so that you knew what nobody else knew, that there was something special about what was otherwise uniform. And I think that my own practice, one of the things that I delight in are many of the hidden details, and so I look for those in other work as well. I want to start off with the World Trade Center towers, which were designed by Yamasaki together with the structural engineer Leslie Robertson, who was also responsible here for the Bank of China. As you know, perhaps, the structure of this was quite innovative. It's a perimeter frame made up of closely spaced columns and beams, and it was fabricated out of a kind of Lego set of these elements 3 stories tall that were sometimes called trees, that are made up of box sections for the columns and actually just plates for the beams. These were all customized. It's common in Les Robertson's design structures that the elements are generally quite specific and quite customized. The same is true for the Bank of China. And that made up the framework. A couple of years ago, with a class, now about 10 years ago, with a class at Princeton, we put together this drawing. In fact, Adam Frampton, who was until recently working at Omei's office here in Hong Kong, helped with this when he was a student. It shows, for both of the 2 towers, the distribution of the steel that Robertson placed in different parts of the structure. Going back to this, the box columns are made out of plate. As I said, the beam is made out of a single plate. The thickness of those plates and the type of steel varied as you moved around. The actual dimension of the column, the outer dimension of the column, and the size of the plate, not the thickness of the height of the plate, was the same throughout the system. So the only variable were thickness and steel type. And what's really interesting and subtle about this design is that what Robertson was doing was using higher strength steel, as shown here in red. There were 14 different types of steel. The higher strength steel was being used in order to make the section size, the thickness, smaller. And by doing so, make an element less stiff than its neighbors. So the corners were where he used the higher strength steel because it was a way of shedding the load away from the corners into the face of each building. The purpose of a tube frame is that you mobilize an entire perimeter of the structure in a tube. And so to do that, you want to make sure that the forces don't cluster around the corners, which they have a tendency to do. So making things smaller, he was able to shed load and move them to other parts of the structure. Now, in addition, because these 2 towers sit in the city, they sit in a particular relationship or sat in a particular relationship to each other, the wind environment around them is different. And so they get affected by the wind either coming across the water or coming across the city in different ways. Same situation here with their upcoming typhoon. And also they're affected by their relationship to each other. One shelters the other in certain kind of wind condition. All of that was studied using wind tunnels. All of that was then integrated into this design as well, because what you're seeing is the steel that's required for the maximum envelope of all the possible conditions of wind affecting these towers. So you have displayed here, or in fact not displayed in the building, but displayed in the diagram, a mapping of the environment, a mapping of the will of the engineer to distribute things in a particular way, and then a very innovative way of using a large variety of steel to move forces around. What I love about this is the fact that this was completely hidden and unknown to most people until we did this diagram. I helped curate a show at Museum of Modern Art, also about 10 years ago, on tall buildings, where we displayed this as one of the installations. This shows the wind tunnel model. This was one of the very first wind tunnels models used for a building. So there's something in this building that requires a fair amount of care and attention and study in order to reveal, but which once you see it, becomes, I think, a significant influence on other work. This is the diagram where it lives now, just behind the garbage, and next to this beautiful Pissarro painting in storage at moment. Another idea that I think is important, and it direct influence from literature, is an idea that Edward Pound termed vortex. His definition, it is a picture that means 100 poems, the music that means 100 pictures, the most highly energized statement, a statement that has not yet spent itself in expression, but which is the most capable of expressing. A vortex is a kind of node of energy. His definition, the tempo malatesta and Rimini, which if you're not familiar with, is worth studying, was this gathering of terrific and interesting patrons. He was Nuda Malatesta, Alberti, for whom this was one of his first commissions, and a number of very, very capable artists, including Piero della Francesca, who Alberti brought to the project. It was for Pound a significant representation of this idea of vortex, that there are moments of history that are very significant because an opportunity is created to do a great piece of work, and when you deconstruct that moment and deconstruct that work, you're deconstructing also a significant point in the historical current. For me, a similar situation is the Menil in Houston. I'm actually working now with, Clover Lee, her brother, Mark, and his partner, Sharon Johnson, wanted commissioned to do a drawing center right next to this building, which is great to be working nearby. This is the Renzo Piano, Peter Rice project now 20 plus years ago for the Menil. The significance of this project, I think, is the fact that besides being a terrific building and maybe one of Piano's best, it was a convergence of many interesting, very significant, I think, cultural factors. Patron Dominica Menil had a significant influence on the project. She, in turn, had worked before with Philip Johnston, whose influence on her through a house that she did with him played into this project. She had also worked with a man named Couturier, who was a Dominican monk who advised her when she started collecting art, who was responsible for the commission of Le Corbusier to build the Champ and of Matisse to build the chapel of Saint-Paul-de-Vence. So there were several currents coming together in the client herself. In addition to that, she had commissioned Louis Kahn to design the museum, but the commission was halted when her husband died, and then Kahn died. So when Piano came, there was the history of Kahn, his connection to the Kimball, Piano's connection to Kahn, worked briefly in Kahn's office, and so on. And then on the project itself, you had a director, Pontus Hilton, who recommended Renzo Piano, who had been in charge of not only the Pompidou Center for the Great Museum of Denmark and Louisiana, as well as art advisor Walter Hopps, who brought the first exhibition of Marcel Duchamp to the United States. I could go on and on. There's lots of currents that come together, which are a significant part of what made this building, I think, what it is, similar to the Tempio in Rimini. And then, of course, the design team, which consisted not only of Renzo Piano, but Peter Rice, the great structural engineer, and also Tom Barker, his partner, the mechanical engineer, who invented the displacement system. You see the grills down in the floor there, bring the air in and allow it to move up onto the ceiling, which is made of these leaves, which are part of the structure, devised by Rice and Piano, which is a composite of the Ferrocement leaves, which serve as light baffles, but also as the bottom chord of these trusses. And then the top diagonal members are made of cast ductile iron, both very innovative materials not used in any other project. So there's a tremendous care and attention to invention in every aspect and detail of this project. The space between the glass that you see on the roof and the trusses is used to capture hot air in the winter that is then pushed down into the underfloor air and used to heat the building. It also gathers the air in the summer and lets it vent out. So many, many different aspects to this that are quite interesting and significant and deserve close reading and close analysis. This is the leaves and fabrication. They were made actually in England. But the system basically comes from the making of boats. Pier Luigi Neri's influence as well is present. It's sprayed on cement and sand and water mixed together onto a lattice of fine bars. These are the castings that were made for the structure above. Both of these projects, I think, represent, cases where there's a tremendous depth in the development of the ideas, some of which is visible on the surface, some of which is completely invisible, and yet present, I think, in the significance or meaning of the project. Now, I want to run through projects of ours over the last 20 or so years that fall under a couple of different categories, which I think are useful. One is this category of simply supported. There's a long history in modern architecture of seeing engineering work as a kind of necessary diagram of forces which, when mobilized for the purposes of architecture, can lend authenticity to architecture itself. So the simplicity, clarity of the representation of the structure is seen as an important contributor to the authenticity of work. And you can see that in Gideon and Frampton and many other writers throughout the 20th century. Simply supported then is meant to capture that idea. I think it's more complex and more interesting than a simple representation of the structural diagram, but I think it's an interesting way to start. This is a building competition that Stephen Hall won that we worked on together for a library in Berlin. And so I want to run through 9 projects here briefly that represent this notion. The first is a writing rink, which I worked on with Jack Robertson, who at the time was partners with Peter Eisenman, which is an upstate up in Connecticut. It's made of wood and steel members that are deployed in a three-dimensional structure that spans over this space. The steel is fairly simple, fairly rudimentary detailing. The wood is blue laminated, there's a wood deck on top of that, and then the steel rods go up and over and tie that structure together. The second, which really, I think, captured this idea of simply supported, this was a little project with Roy Hawkinson and Henry Smith Miller as part of an installation at the North Carolina Museum of Art, where the support is trying to represent very directly the conditions of equilibrium of a simply supported beam. So one side able to move and rotate, the other side prevented from going up and down. So a kind of caricature almost of the structure. The Santa Fe Opera House in New Mexico with Jim Polchek. This was a project where we were asked to design a new roof to sit on the existing structure of the old opera house, and so we had to keep it as light as possible. It contains a fly space, which you see on the left there under the suspension structure, and it's an entirely closed structure, whereas the previous one was open places to the rain. These props then sit on 4 columns and then are spread out to hold up the, so there's like 2 B's, upside down B's leaning against each other, and from them the system of cables that supports the edge members of this structure. There's a clear story connecting the 2 roofs, one over the balcony and one over the main space. This was a little folly for Museum of Modern Art, an exhibition that Terry Riley organized called Fabrications, which I did with Enrique Norton. It faces the sculpture by Rodin of Balzac, and so Enrique's idea was that you sit in this chair and observe that. And I did this little canopy over that, which is made of glass, laminated, and then used as a compression element in this little simple structure. So the cable puts the glass in compression, pushes back at the bottom end there, which is resisted by those 2 struts coming up, which also then pull up on the space below. And then the backspan comes down, and you can see the bottom left there, there's lead support, big weights of lead that create the counterweight for that. It was a temporary structure, so it was done with a very minimal factor of safety. The text was taken from Maria Rilke, a book that he wrote about the Rodin of Balzac and printed on laminate. One of the interesting things that happened with this was for cost reasons, the glass manufacturer convinced me that we could get away with a layer of tempered glass and a layer of annealed glass laminated together, which was fine because the tempered glass was taking the force, which is being transferred here in the detail on the right. The problem was that due to the concentration of stress, the laminated glass cracked pretty soon after the installation was put in. I didn't find out until later why it cracked, but the crack was there. And that led to an interesting predicament where I said to the museum, well, if you're worried about this, maybe we should call in somebody else and ask them what they think, get a second opinion. And smartly, the museum people said, well, second opinion is going to tell us to take it down. So you just tell us what to do. So I rigged up this thing that I would install in the event that there was a windstorm coming through. So I had it ready, and every morning I would check the weather for 4 months, worrying about what would happen, praying that everything would be all right, which it was. In the end, at the closing party, one of the guards came up to me and said, I've been meaning to tell you why this happened. Apparently, one of the days that he was on shift, he caught a guy who jumped up, grabbed the leading edge of this thing, and was doing pull-ups off the hand. Don't touch the art. This was this museum with Steve Hall in Iowa. It's sorry, not a museum. It's a school of art history and art for the University of Iowa. This had in Iowa City. It cantilevers out over an old quarry which is filled with water, and in that cantilever structure is the library. We built these oversized trusses with gigantic plates, kind of Puzzle-Lumberg version of a truss. Didn't do it actually on purpose. What happened was we drew these details, and I don't think we quite had a sense of the scale of them. And then they were built, and Stephen was quite aghast when he saw them, but it was too late. And now we've all kind of gotten used to them, and they have a nice comic feeling. This was a very inexpensive building. We were able to build this building for $200 a square foot. The stair was really a direct translation of watercolor that Stephen made, so there's really quite a wonderful comparison that can be made between this watercolor and the stair. It's all made with folded steel plate hung from the top. It's quite a beautiful stair. Also with Stephen, the Nelson Atkins Museum in Kansas City, it's a series of glass prisms marching down the landscape alongside the old museum, and then a garage that sits behind the old museum with a sculpture by Walter de Maria on top. The system for the glass lenses, as they're called, is all centralized. So each of them has a spine structure down the middle, and then the roofs cantilever out and are stabilized with smaller members in the perimeter to keep from interfering with the light. So you can see a little bit of the truss on the left is visible, and then the double glass wall on the side you can see that you can barely see any of the structure in there. So we tried to minimize the structure by cantilever, a little bit like a mass structure where you have a central pylon and stays. This is in Memphis with Coleman Coker. Used to be partners with Sam Buckley, very, very talented architect in Austin, Texas. This was for a community center in Memphis called Bridges. Bridges, for the community and metaphoric meaning. And so, of course, we had to build a bridge-like structure for that. And then for the slab, we came up with a system of very skinny columns supporting a steel cap, kind of like a capital, so that allowing us to use skinny columns with a concrete slab. There's a climbing gym inside that truss structure. For competition in Washington with Harry Cobb, this was won by Norman Foster and built. It's a courtyard for the Patent Office building. We came up with a design based on the moment diagram of a flat plate supported on 2 points with 4-pronged feet, like so. And the basic principle you see here on the right is you take the grid, you plot the moments in that grid, and then you use that geometry to create a system of tubes that follow the geometry in both directions, so that if you run a series of cables in those tubes and post-tension those cables, what happens is that exactly balances out the self-weight of that roof, and the whole thing is flat in equilibrium between the weight and the distribution of forces from those curving cables. So it's a kind of pre-stressed, or actually post-tension system displayed and turned into that pattern. A little bridge in New York that we designed, made in wood and steel. These are steel plates underneath that reach up with these little tabs and then are bolted together with the wood to create a composite Diradel truss, kind of like a little piece of furniture in a loft in New York. So that's a simply supported category. So you can see in each case there's clearly the overt representation of a structural diagram, and I think in some ways it draws you in, and if you're interested and curious, you can start to disentangle some of the layers of meaning beyond that. The second category is what I call engineering ephemera, and that is places where much more is hidden. So, for example, with the museum competition at Student Hall 1 for the museum Helsinki back in the 90s, Kiasma, we, for the first time with Stephen, we developed a strategy where we made a thick wall, kind of pochette wall, which could be used to distribute the campus system. So, you know, like you see here, often you distribute the system in the ceiling. We took that package and bent it into the form of the building. And there you see the trusses that reach up and over to make that shape are also then the void, the pochette, where all the campus systems are distributed into the building. This is a little canopy at LaGuardia Airport in New York, did with Lori Hawkinson and Henry Smith Miller. This was an investigation of how to use carbon fiber and glass fiber reinforced composites to make a shade that is then tied to a steel structure. This is kind of a homage to the menil, but flipped in the other direction. So this is a composite structure spanning between cables that are suspended back to the columns. You see there's also a glass triangle that is the mediator between the cables supporting the system and the trusses. At the Menil, a project with François de Menil, son of Dominique de Menil, this was a chapel to present some frescoes that had been recovered from thieves that had stolen them in Cyprus. They were recovered in Germany, reassembled, restored, and on loan to the Menil until last year. So this was about 15 years, and the design here was to recreate the chapel which they lived in Cyprus out of laminated glass plates. These are not tempered glass. They were too big to be tempered, and they also needed to be sandblasted. So the system here has to attach to the glass with these little clips without putting holes through it. If you want to put holes in glass, you have to use tempered glass. So here we devise these little clips to hold the glass in place. It's held in place against this kind of spider web of rods, about an inch, 3/4 to an inch in diameter, black rods, that are stretched between the ceiling, roof structure, and the bottom. So the whole thing is pulled taut, and that gives it stiffness. There's actually a system of springs up at the top that makes sure it stays taut, even if the roof were to deflect in the wind, and that holds everything in place throughout. This is the disassembling of that. So here's a structure where I designed both the structure and its construction, and then designed the film in the other direction. With Architectural Research Office, a little stair, which was in a loft in downtown New York. This is based on a model that goes back to the Renaissance that Palladio used and others to cantilever so-called stairs off of one wall. And the way this was done by, this is Palladio's stair on the left at the Academia in Venice. This is an even older stair I saw in Greece on Milos Island. The system is one where you take each tread and overlap it slightly with the one below, and so on as you go up. You see that clearly on the right. And what that does is allow each tread to lean on the one below, so they're not actually trying to cantilever off one end because they're leaning. But because you're getting a force applied at one side and a reaction on the other side, there's a twist that happens, and the twist has to go back into the wall. Now, the stone can take the twist,
If these weren't engaged with each other, the stone would not be able to cantilever. Stone doesn't like to cantilever, doesn't like the tension associated with that. So this was an invention that masons came up with in the Renaissance that has been applied off and on over the centuries ever since. What we did with this design was to apply that principle, but use a glass wall instead of the typical situation. And so here the treads are actually steel, the treads are actually aluminum plates. The risers are these steel tubes. You can see the plate going from the bottom of one tread to the top of the other tread. So it creates a continuum of each leaning on the next, and then the twist goes through that tube into the glass. And here's a physical test that we did. And here's our most famous occupant of that stair during the fundraising. It worked for him. With Sana, Seishiman Nishizawa, we did the Toledo Museum of Art in Toledo, Ohio. Here, one of the most interesting aspects of this, I think, is the fact that the structure just completely disappears. The columns are very skinny, as is typical, but they're also distributed in a pretty irregular geometry, and so you really can't read the distribution of the structure throughout. Very thin structure, a lot of work in integrating everything into that thin sandwich. On the left is a model of the original design, and the entire system of that roof structure is continuous. So everything is rigidly connected to everything else, so it operates as a kind of rigid grillage or blanket over the entire system. And that's the fit up of the glass. Very, 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 very tight tolerances. We had a lot of effort in putting everything together and getting it all to fit. Also with Sana, the new museum in New York, kind of the flip version of this, the walls are very thin and the walls are the primary structure, which serve as belt trusses that take the load as the boxes shift relative to each other down to the ground, and they're exposed as well. And in a similar vein, a house we did with young architects Stella Valley and Bernheimer up in Connecticut. We used very thin pieces of plywood to make the roof structure, similar to the Sverfen Pavilion in Venice, the Nordic pavilion, so letting the light filter through very closely spaced blades of structure. That's them. So these are plywood laid as beams and ganged up with these tubes to create prefabricated units. And then the other thing you can see here on the left is the whole thing is hovering above a glass wall where you cannot very easily tell where the structure is. And this is a trick that we played a number of times where we use the mullions as the columns. So in effect, you lose the reading of the columns, they disappear. Down here on the left, this is at the World Trade Center site. We actually did the Goldman Sachs headquarters in the back there, as well as the slurry wall. Here you see face on, which is part of the museum. There was a desire to expose the structure. After lots of back and forth, we came up with a system of buttresses back behind the wall in the ground, so the support is completely invisible in that case. So that's the wall as it was, and then we have a series of buttress structures behind that. A bridge at Yale we did a couple of years ago based on a Victorian model. We used a kind of lattice structure here made out of plate, which was corrugated with varying wavelengths to correspond to the effects of the forces. What we're trying to do is use the corrugation as a means of bracing the top part of this beam. The railing is the beam, and if you think about it a little bit, remember your statics, when you have a beam standing across like that, the compression goes in the top, and because of that compression, if it's not well braced, it wants to buckle to the side. So we use the corrugation that you see here in the middle to brace that, and at the ends to keep the web itself from buckling if it's quite thin. There's a 1/4 inch thick web. So a lot of cases in this instance where things aren't visible, and if you're interested, you really have to dig deeper to understand what's happening. The final category is one that I call making history or building history, which has to do with using the process of construction itself as a generator of meaning and memory. This is an installation of a sculpture by Glenn Cedar at the Museum. So here, I think there's a number of different ways of thinking about the problem. This is the Austrian Cultural Institute that Raymond Abraham designed in the competition that he won for this building. Here, it's really kind of, it's typical of his work as a kind of representational building. Almost looks like an Easter Island statue standing there on this lot with very figural expression. The structure is made up of a C-shaped concrete walls on the side and in the back, and then in the front you have a system of diagonal braces which allow for openness, and the braces are not fire protected, and that was done because we were able to convince the building department that we didn't need the braces for the building strength, we only needed them to control vibrations. And so you see the figure of the braces behind the wall. I don't think you can see it that well here, but the figure of those braces actually looks like a kind of Vitruvian man. So there's a kind of representational aspect to the braces as well. In Stephen Hall's dormitory at MIT, Simmons Hall, we developed a perimeter structure made out of concrete, a grid of concrete, precast concrete elements. And here, a big part of the charm of the building, I think, is that the construction method itself was quite theatrical and exciting. So we went through a number of iterations before we got to this approach, but Stephen's metaphor for the building was a kind of sponge, and so that revealed itself in these odd voids that were popping out, but also in the kind of perforated quality of the surface. So we made that out of the concrete grid. We developed a design that reflected the pattern of stresses and concentrations of stresses that happened because of the various openings and cantilevers by filling in some of the squares in different places in order to give it more strength. And there was a really interesting iterative process where we would fill in the square, the distribution of stresses would change, and we would be led to a certain pattern, and then we would look at that pattern with Stephen, and if it wasn't quite right in terms of where we needed windows, we would go back and adjust it, and then go back through the whole process. The prefabricated panels were joined with the rebar coming through connectors, and also the concrete slab coming out and filling in between, a kind of mortar between those panels. The actual legs and horizontals of this grid were all the same, geometric. It actually changed. It was 12 by 12 in both cases up to the halfway point, and then 10 by 12 above that halfway point. So the only thing that varied was the rebar inside, and the rebar was always 4 bars, but the size of those bars could change. And so here, what we did was very, and you see this has some similarity to the World Trade Center diagram, though this came a little bit before, actually. I think this must have led to my thinking of drawing that diagram. But what happened was that the diagram you see at the top was generated by Amy, the site engineer, who was checking to make sure the rebar was the right size in each of these elements. And so she would have this diagram to make it easier for herself to check it. I took that to Stephen, who wanted color in the facade and had been looking for various patterns, and we ended up using that as the basis of the pattern. So what you see in the color pattern is a representation of the steel type or size, which in turn is a representation of the stresses. So I have a fantasy that someday, and you only see it from the side. It's in the jamb and the head of the aluminum that makes up the cladding. I have a fantasy that I'm going to get a letter someday from a student at MIT who's going to tell me that shouldn't be red, that should be blue. So, no, I haven't gotten that letter yet. This is the church in Rome with Richard Meyer competition that we won together. And it's made of these 3 concrete shells that are all cut from the same sphere and that are facing south and bring the light into the space. And what we did here was fairly adventurous, but again created this very dramatic construction process. And that was to make the walls out of large precast concrete blocks. They're 2 meters square, 87 meters thick. They were prefabricated in northern Italy and brought down and stacked up with this giant gantry called La Macchina, which went back and forth, installing these slowly over time. It took about 2 years. Kids were growing up in the neighborhood watching this thing go back. All of them have undoubtedly become architects and engineers as a result. The machine was digitally controlled and would lift the piece up and then flip paste them exactly where they needed to be. We worked briefly on the World Trade Center tower in 2003 and developed a design which was half tower, half building with a diagrid structure for that, and a lot of work looking at wind turbines in the upper part. This is a memorial for students that died at Texas A&M in a bonfire made out of blocks of stone just doweled together, so unreinforced, very much trying to be in the Stonehenge solid block language, not doing these out of reinforced concrete. So worked very hard to see if we can make these things out of solid stone. This is the exhibition at CUHK where we studied the possibility of camber, where you would take a laminated metal beam and make it in the shape of its desired deflected shape. This is 40 feet long, hung from 2 cables, and so we pre-shaped it so that in theory it would come out level. Of course, it never quite happened. Some of them failed, but by the time we got to the one on the left, we were almost there. So it's really an investigation in how to get something to be perfectly flat and compensate for the way it wants to deflect under its own weight. Finally, there's a tower we worked on for radio tower, for television tower for New York, which is a collection of tubes arranged in such a way that they shield each other from the wind. So they, watched during the Tour de France, bicyclists like to work in, they call the peloton, the groups where they provide shelter. The lead guy provides shelter for the other guys who get pulled along in the draft. And so the same idea here is we tried to orient the tubes in such a way that they would face their least resistance toward the greatest direction of wind. This is actually back to the Nelson Atkins Museum. This is a garage under the Walter de Maria piece, which is made of a series of long, specially made prefabricated concrete beams, what we call wave T's, which create this corrugated feeling on the space below, each individually supported by columns, so that there's no interruption of the flow of this space in the other direction. Near to here in Nanjing, we finally completed a project with Steve Hall for a museum there, which is hovering up in the air, made of a truss system propped on these legs, as you see here. So in all these cases, actually the historical part of this thing is that they built this part, and it sat there for 3 years, so we have all these great photographs of it in the snow. It's kind of our own version of the Monet haystack. Okay, I have 5 minutes. I want to run through 3 recent projects as well. So to summarize this last point, there are different ways of understanding and reading structures, I think, that include recognition that the making of it, the process by which the thing is made, the theatrical dimension, if you will, of that process, can itself be an object of design. So you can decide you want to make something out of large blocks of concrete because it's going to be a whole lot more fun to build it that way and a lot more dramatic than doing it some other way. And I think that's an important value to take into consideration, as well as some of the other terms that I pointed to. So we recently completed in Fort Worth with Renzo Piano the Kimball. Very challenging project across from Louis Kahn's building. Renzo's approach was to build a pavilion, now called the Piano Pavilion, which has behind it a semi-buried structure which has some other facilities as well. So trying to keep the presence of the new building modest in relationship to what is now called the Kahn Pavilion. As you know, perhaps the Kahn building is significant for a lot of reasons, including the structure designed by August Commandant with Kahn in a series of cycloid-shaped concrete shelves that span 100 feet using curvature as a beam. And so what we needed to do was come up with a system for the structure across the way that had a similar presence but wasn't trying to obviously do the same thing. We went through a lot of iterations where we looked at steel and glass ideas. We eventually decided, in fact I proposed that we try working with wood, which seemed to be both consistent with Piano's earlier projects, but also the right kind of lightness and presence across the Kahn. So we have also 100-foot spans. Plan of the building that Piano did is very much the same arrangement as the plan of Kahn. 100-foot spans for three times. So here we're using the beams. You can see there on the end, the beam is really precariously propped on top of the concrete column, and that is purposeful. What I was trying to do is make this thing as delicate and precarious looking and feeling as possible. The other thing that was important was that the structure had a presence in the space, which is obviously the case in the Menil, but hasn't been true in many of the museum projects for various reasons that Piano has done since the Menil. And so here, clearly, in relation to Kahn and his approach to the relation of structure and light, it was important that the structure have this presence as well. So the wood also has a nice feeling in that regard. So here, the other aspect of the wood, which is really an advantage, is that it allowed us to have the structure go from inside to outside without worrying about cold bridging, because wood is a natural insulator. So there are a lot of features to the wood that were beneficial. The structure is made of these two 8-inch by 52-inch deep, so what is that, 20 centimeters by 125 centimeters, two side-by-side beams which are coupled together with a fairly intricate system of plates, fabricated plates that tie them together. Here you see there are face plates that hold them in, and then inside there's a system that holds them together. And the purpose of that is to allow them to brace each other against lateral buckling. There's nothing holding them from rolling over except that connection between them. This is in fabrication in Canada. All those connections were routed into the wood with a machine tool that was numerically controlled. There you see the elevation. Also, not only do the beams individually, as a rigid body, the beams could want to roll sideways. That's prevented by that tube that you see at the end, so pretty delicately held in place by that tube, so it doesn't roll over as a unit. And then in addition, the beam itself at the middle of the span where the compression is high wants to roll over, and that's prevented by the coupling of the beams together. It's all kind of behind the scenes, if you will, but there is a precariousness to this system to anyone who is able to read it carefully, which is completely intentional. This is under construction up in upstate New York. It's a museum designed by Tom Pfeiffer for Corning glass, which has a system of very thin concrete beams that we proposed on the basis of, again, the Sphere Fen Pavilion in Venice, which everybody loves. And so here we were able, together with a great manufacturer, Quebec, prefabricate precast beams that are 3 inches, 7.5 centimeters thick, 4 feet deep, so 1.2 meters, and about 20 meters long. So very skinny, very precarious as well to create this roof system. That's them going into place. So it's quite dramatic. The concrete work was also very, very good. And so they have a beautiful quality in the light. The entire roof is glass, so the light is being filtered through these elements. And the walls wiggle around to create the space, and they're concrete, and they're supporting the slab below them from above. So the space underneath, which is offices mostly, is all column free or wall free. because all that structure is being provided by the walls above, which are open to the cavity between the walls, which allows the air distribution to happen as well. That also is true at the Kimball. We have cavity walls for the air distribution made out of concrete, which is tricky to get cavity cast into the concrete that allows you to then push the air through that. Finally, this is the last project I'm going to show you. This is a lattice that we just completed in Napa. Just went through an earthquake. Lattice did okay, but the client's wine collection did not. But this was a design for an independent lattice that does not connect to the building around a house, and this is made of bent wood, very carefully crafted, linked to aluminum beams as well. There's a variation in the geometry of the wood. There's some larger openings and smaller openings, and it's all bent, laminated, and fabricated very carefully. Lots of different pieces that come together for this. This was made up in the state of Washington by a great, wonderful fabricator that we started working with up there. So, really very strong reliance on craft to achieve the connections and the structural properties that we're looking for. Voila.